Welcome back. In Part 1, we described the history of the development of the Big Bang theory of the universe and talked about the assumptions behind it and some of its observational consequences. We now continue our discussion and try to make some connection to the ideas about the nature of the expansion and the curvature of space-time. The geometry of the universe depends on the total density of matter and energy that it contains. We know that there are three particular geometries that can occur if matter is distributed homogeneously and isotropic on large scales. Then the curvature of the universe must also be homogeneous and isotropic on large scales. This is the cosmological principle. The universe can be spherical with positive curvature. This will occur in Einstein's theory of relativity when we have a high-density universe. When the density of matter and energy is high enough, it will cause the curvature of the universe to be positive, and a high-density universe will be a finite spherical universe in which parallel light rays converge. If the universe is very low density, then the universe will have a negative global curvature, and we will find ourselves living in an infinite hyperbolic universe in which parallel light rays diverge. In between the high and low density, there is going to be a critical density. The critical density will be the density that the universe will have that will make it exactly infinite and flat. A Euclidean flat universe has no curvature, and light rays will stay parallel over all distances. Density determines the shape of the universe. High density will be positively curved and spherical. Very low density will be negatively curved and hyperbolic. And in between, there will be a critical density at which there will be no curvature and the universe will be geometrically flat. The total matter and energy content of the universe is measurable. We measure it and define what we call a density parameter, omega naught. Omega naught is defined as the total density of the universe divided by the critical density that's required to make the universe geometrically flat. And the little subscript 0 here is the recognition that we define this density parameter at the present time. We make an assay of the energy density content in the observed universe. This is the total density, and it is in principle observable. And we divide that by the critical density, how much matter and energy density the universe must have to make it geometrically flat. If omega naught is greater than 1, then the total density is greater than the critical density to be flat, and we would live in a finite spherical universe. If omega naught was less than 1, then the total density of matter and energy in the universe would be less than the critical flatness density, and we would live in an infinite hyperbolic universe. And if omega naught is identically 1, if the total density of matter and energy is exactly the critical density, then we live in an infinite flat universe. Which these is depends upon what our observations of the universe are going to be. The density parameter, omega naught, is going to be one of the important parameters we need to measure to understand what kind of universe we live in the context of the Big Bang model. Another question that can be asked of the expanding universe is how long has the universe been expanding? Consider two galaxies separated by a distance d as we see them today. The Hubble law tells me that the velocity of separation between these two galaxies will be equal to the Hubble constant times the distance between them. The time of travel that takes for these two galaxies to get that far apart should be how far apart they are divided by their velocity. This is a familiar idea from taking a road trip. If I'm trying to take a trip up to Toledo, Ohio from Columbus, and I know I can travel on the highway at about 65 miles an hour, how long is it going to take me to take the road trip? Well, how far is Toledo from Columbus divided by how fast can I drive? That tells me how many hours it's going to take me to drive from Columbus to Toledo. So too, we can apply a similar calculation to the expansion of the universe. If today these two galaxies are a distant d apart, and they're moving at a speed v, given by the Hubble law, h naught times d, how long have they been traveling to get that far apart? How far back in the past do I have to go when they are on top of each other? The time of travel is equal to the distance traveled divided by the velocity. Well, for these two galaxies, that will be the distance apart, d, divided by their velocity, which is given by the Hubble law, h0 times d. You'll notice that d appears both in the numerator and denominator of this ratio, and so the distance cancels out, and the time of travel is just 1 over the Hubble constant. This allows us to define a parameter we call the Hubble time, t0. t0 is mathematically 1 over the Hubble constant. It is how long the universe could have been expanding before to get the galaxies out to the distances with the speeds we observe they have today. This assumes that the expansion rate is constant, that the Hubble constant is a constant not just now, but over all cosmic time. So this is simply an approximation of how long has the expansion been occurring. For a Hubble constant which we measure locally to be 68 kilometers per second per megaparsec, this would imply a Hubble time, 1 over h0, of 14.4 billion years. Do the calculation and put in the number of kilometers in a megaparsec, and you'll see that it comes out right. We'll leave that as an exercise to the listener. This tells us that in order for galaxies to be as far apart as we see them today, with their observed redshifts, with their observed cosmic expansion speeds, the universe has to have been expanding for at least 14.4 billion years if that expansion rate is constant and unchanging through cosmic time. The Big Bang Theory also has another implication that might be surprising. The Big Bang Theory naturally explains why the sky is dark at night. You might think that's an obvious answer. Well, the sky is dark at night because the sun's not up, of course. But there's a greater mystery. Why is the sun dark at night? If the age of the universe is approximately the Hubble time, which is 1 over the Hubble constant, then light from stars farther away than a distance, the speed of light multiplied by the Hubble time, or the speed of light divided by the Hubble constant, will not yet have had time to reach us. The way to think of this is as follows. Imagine an infinite universe filled with stars all spread out through space. Eventually, if the universe is infinite and has lived for an infinite time, then one of my lines of sight will eventually intersect with the surface of a star. No matter what direction I look in, eventually my sight line is going to land on the surface of a star, and so I should see the light from those distant stars. The analogy is to think about walking up to a forest. If you stand at the edge of a forest and look into the forest, if the trees are very sparse, no matter how sparse they are, if the forest is very, very large, eventually your line of sight, you will be able to see a tree along any direction you look. If the forest is very dense, I won't be able to see through the forest at all. Like the old expression says, can't see the forest for the trees. If you lived in an infinite forest, eventually you wouldn't be able to see through it, because no matter which way you looked, you would always run into a tree. You would always see a tree or leaves in your way. So too in a universe filled with stars. If the universe were infinite and filled with stars, then every sight line should intersect the surface of a star. This means that the sky on average at night should be as bright as the surface of an average star. Clearly, it's not. This is what's often known as the Olbers paradox. The fact that the sky is dark at night is telling us that the universe is not infinite in extent, or at least is not infinite in extent. If it is infinite in extent, it hasn't been around for an infinite time. If it has had a finite lifetime, then there won't have been enough time for stars to have reached us from beyond this distance, c over h0, which is called the Hubble distance. The fact that the Hubble distance is a finite distance is why the sky is dark at night. The correct solution of this Olbers paradox was found not by the discovery of the expanding universe, but was first correctly described by the writer Edgar Allan Poe. Nonetheless, the Big Bang Theory correctly predicts that the sky should be dark at night, a seemingly obvious thing with a very profound consequence for its explanation. We define the Hubble time in terms of the assumption that the cosmic expansion rate is constant. But the cosmic expansion rate is not expected to be constant over all times, and indeed could be faster or slower in the past. For example, if the expansion of the universe were faster in the past, then the Hubble time T0 will be an overestimate of the expansion age. If the Hubble time is about 14.4 billion years, but the universe was expanding faster, then it will have taken less time for the universe to have gotten to the galaxies to the distances and speeds we see. Again, let's use our road trip analogy to understand this. If I compute that traveling at an average speed of 65 miles an hour, it's going to take me 2.5 hours to drive to Toledo, but somewhere along the way, I put my foot down on the pedal and I drive 85 miles an hour at the beginning, and then I hit some road construction and I slow down to about 55 miles per hour. Even with all those things put together, I might actually reach Toledo in an hour and a half instead of 2.5 hours. Hopefully I won't get a ticket along the way. But as a consequence of having driven fast at the beginning and slow towards the end, I nonetheless reach my destination earlier, because my measurement of my speed now is not a representation of the speed I was driving over the entire trip. So too with the expansion of the universe. If the universe was expanding faster in the past, then I will have reached galaxies at their observed distances with their observed speeds earlier than I would if the expansion of the universe was constant, and therefore a faster expansion in the past will mean that the Hubble time overestimates the expansion age. However, if we lived in an accelerating universe, in which the expansion of the universe was slower in the past and faster in the present day, then it will have taken me longer to get out to where I am, and with the galaxies at their distances and speed as I observe, and therefore the Hubble time will be an underestimate of the age of the universe. This is a little bit of a warning that things are a little bit more complicated. Well, what is it that determines whether the expansion of the universe was faster in the past or slower in the past? It's suggested by the geometry. A spherical universe will be expanding faster in the past. A hyperbolic universe will be expanding slower in the past. Light rays diverge in a hyperbolic universe. Light rays converge in a spherical universe. And if the universe was perfectly flat, that would be, at least in this approximation, a coasting, constant speed of expansion. And now we can see where this idea of the geometry of the universe, which is tied to the total matter and energy of the universe, plays a role in trying to piece together the history of the expansion as predicted by the Big Bang. To estimate the true age of the universe, we must measure two numbers. The first of these is the Hubble parameter h0, which asks the question, how fast is the universe expanding today? The second number is the density parameter, omega naught, which asks the question, how has matter and energy density affected the expansion rate in the past? Taken together, we can include this with a dark energy contribution that could act to accelerate the expansion rate of the universe. So to correctly determine the age of the universe, I must take into account how fast is it expanding today, and through the density parameter, what is the behavior of that expansion in the past? Was it faster or slower than I see in the present day? Just like the analogy with the road trip, to find out how long it really takes me to drive from Columbus to Toledo, I have to know not only how fast I am traveling now, but how fast I was traveling at all times along my trip. When we put all these numbers together, what we find is for the best observations of the density parameter and the Hubble parameter that we've observed to date, our best current estimate for the age of the universe is 13.798 plus or minus 0.037 billion years. 13.798 gigayears. This number assumes that the Hubble constant is 68 plus or minus 1 kilometer per second per megaparsec, and that the density parameter omega naught is approximately 1, which consists of a 30% contribution from all forms of matter and energy and a 70% contribution from dark energy, which we represent by the symbol omega sub lambda. This age of 13.8 billion years in round numbers is consistent with the ages of the oldest stars that we see in globular clusters as measured from their Hertzsprung-Russell diagrams. So far, so good. Our estimate of the age of the universe, about 13.8 billion years, is consistent not only with our measurement of the expansion rate of the universe, the Hubble constant, as seen today, and the total matter and energy content of the universe, which combined with the dark energy contribution tells us how fast the universe was expanding in the past. It's also consistent independently with the ages of the oldest stars that we can see. This number, while successful, raises a lot of interesting questions. The Big Bang raises some questions to ponder. Is the universe infinitely old? Well, you might say, wait a minute. Didn't you just tell us the age of the universe is approximately 13.8 billion years? What we really say by the age of the universe is that approximately 14 billion years have passed since the universe began expanding from its initial dense state. This then raises a question to ponder: what happened before that initial dense state occurred? After all, the true age of the universe might be how it was expanding from the time of the Big Bang, but was there something before the Big Bang that gives us the true age? We're only talking about, in our estimate of 13.8 billion years, how long the universe has been expanding from a hot, dense state. What came before that? What happened before the Big Bang, before the start of the age of expansion that we find ourselves in? Another question to ponder is the universe infinitely large? We don't actually know the answer to this question. We can only see a region roughly 28 billion light years across with no boundary in sight, no apparent change in the structure of the universe that occurs about 28 billion light years away. Because we live in an expanding universe that has only been expanding for about 14 billion years, we can only see out as far as light will allow us to see. This then gives us a question to ponder. If the universe is finite, does it have a boundary? Or is the universe actually infinite in extent? We don't know the answers to these questions, but they're questions that may be addressed sensibly in the context of the Big Bang theory and tested in observations of the actual universe.